Alright, so in this video we're going to be talking about chemical composition. So percent composition, empirical formula, things of that nature. Alright, so let's just go ahead and jump right into an example problem. So they could ask you a question like this, and this one says a 4.5 gram sample of which of the following would have the greatest mass of oxygen. Well, this really goes back down to percent composition. So percent composition is equal to the total mass of the element divided by the total mass of the compound. It's just like any percent. Part divided by whole. And then, of course, multiplied by 100. So, when I'm looking at this, it says that a 4.5 gram sample of which compound. So this is going to be the same. So really, which one has the highest percentage of oxygen? Well, we can't just simply count the atoms. We're going to have to look at a mass percentage. So what we do is we're going to look at the mass percentage of oxygen in each one. And since it's the same amount of the compound, we don't have to worry about this part. Now, if it gave us different amounts, like this one was 4 grams, this one was 3 grams, then we would have to multiply the percent as a decimal by that amount to get the amount of oxygen. So we don't have to do that in this case. So what we're going to do is we're going to look at the mass of the element, which is oxygen, divided by the total mass of the compound. Well, oxygen's mass is 16. And it gives me the molar mass here, which is nice, which is 62. Alright, so I'm not going to try to divide it out right now because more than likely they'll ask you a question like this in the multiple choice part, which means you don't have a calculator. So let's do the rest of them. We'll look at it as fractions. So oxygen is 16, and the molar mass here is 30. And then when I look at this, 16 divided by 40. And then this one is going to be 16 divided by 104. Well, this one is asking for the greatest mass percent. So, really, let's see if I can eliminate any choices without even trying to do any math. If I'm looking at this, it's all 16 out of some number. So the biggest number on the bottom is here. So that means I'm going to get a lower percentage here than here, here, or here. So I can automatically eliminate this one. And also, I can eliminate this one. And really, it looks like this will have the highest percentage without even doing any kind of math. And now, I could have gone through and said, okay, this is 1/2. This is, well, obviously this is going to be less than 1/2, but I could have gone through and tried to say, okay, this was close to 1/4. I could have done that, and if it's easier for you to see that way, then go ahead and do that. But since the number on the top for each one is the same, then I'm just looking at the bottom number. So this will give me the highest percentage here. So it should be B. Alright, so now let's look at something else. Okay, so empirical formula is important. They would probably ask you to calculate an empirical formula in some way. So percentage can be used to determine a composition of a compound. Empirical formula is the smallest whole number ratio. So if I'm looking, H2O, well, I have a 2-to-1 ratio, and then that is the smallest whole number ratio I could have. So that is an empirical formula. But if I have H2O2, that is not the smallest whole number ratio because it would actually reduce down to HO. So the smallest whole number ratio is my empirical formula. Well, there's a couple steps to get the empirical formula. The first would be if you have a percentage, go to mass. So if you have 40%, pretend like it is 40 grams. So that's the easiest part. Now, if they give you percentage, most of the time they probably won't give you a percentage though. Most of the time they'll give you some way to get mass. They'll probably give you some lab data, and you have to figure out what the mass is based on that data. The next step is to go mass to moles. The next step after that, divide by small, then multiply to a whole. More than likely, Don't quote me, but you probably won't have to do that last step. Usually most of the math works out that once you get the number of moles, you're going to get the ratio by dividing by the smallest, and then usually you have whole numbers at that point, so you don't have to do this part, usually. Basically, the empirical formula is a ratio. Remember that? It's a ratio. So it's a molar ratio. So we need to know how many moles of this versus how many moles of that. And then that's why we divide by small. We're trying to find the ratio. So basically, if you find they want you to calculate the empirical formula, you need to have the mass or the number of moles of all your components. So normally they will give you lab data and you will need to figure out the mass or the number of moles of each of the components to get your empirical formula. Now the molecular formula is the actual number of atoms. So this can be a molecular formula, but not an empirical formula. So the actual number of atoms will be the molecular. So to get the molecular formula, if you're given an empirical formula and they ask for the molecular formula, you would need the empirical formula, the mass of the empirical formula, and then the mass of the molecular formula, which they have to give you some way. So once you have that, you're going to get the ratio of the masses. So basically determine how much larger the molecular compound is, and then multiply that number by the number of atoms that you have. So let's say that we find the molecular mass is 4 times as great as an empirical mass. And let's say this is my empirical formula. Well, if the molecular mass is 4 times as great, it has 4 times the number of atoms. So I would multiply the number of atoms by 4. So the molecular formula is the actual number of atoms. The empirical formula is the smallest whole number ratio. All right, so this is an example of what they might give you. And like I said, most of the time they're going to give you lab data. So when 10 is treated with concentrated nitric acid, the resulting mixture is strongly heated and only remaining product is an oxide of 10. Basically that means it's 10 and oxygen bonded together in some ratio. The student wishes to know whether it's SNO or SNO2. We're going to identify the compound. So if we want to know it's this or this, we need to know what the empirical formula is. Anytime we're looking for the empirical formula, we need the mass of each of the components. In this case, I need the mass of 10. I need the mass of oxygen. So let's figure out what that is first. Okay, so I'm given the mass of pure 10, so I have the mass of that. It's 5.20 grams. Now I need the mass of oxygen. Well, I heat it up, and basically the 10 reacts to the oxygen. So after I heat it up, I should have 10 oxide. It's either SNO or SNO2. So this is the mass of the 10 oxide plus the crucible. So let's find the mass of the 10 oxide. So to get the mass of the 10 oxide, I'm going to take the mass of my crucible with my product and subtract out the mass of the crucible. Well, when I subtract that out, I get 6.602 grams. But remember, this is the mass of everything together. The mass of 10 by itself should be 5.20. So I need the mass of just the oxygen here. So what I'm going to do, I'm going to subtract the mass of the 10. And then that's going to give me the mass of my oxygen, which is 1.402 grams. So in order to get empirical formula, you have to have the mass of each component. So if you have lab data, you need to get the mass of each of those components from that data. All right, so now what we're going to do, the next step is to go mass to moles. So I need to know how many moles of each thing I have. So let's do SN. I have 5.20 grams. All right. 1 mole over so many grams would give me, well, the molar mass is 118.71. That gives me 0.043. All right, I'm going to do the same thing for oxygen. So when I do that, I'm going to get 0.087 moles. Well, the next step to get my empirical formula is divide by small. I am trying to find the ratio of 10 atoms to oxygen atoms. So I pick the smallest number, I divide both of the numbers by the smallest. All right, so I get 1 here, and then here I get 2, or roughly 2. All right, so it looks like I have a 1 to 2 ratio. Well, in that case, that means I have 1 tin atom for every 2 oxygen atoms. All right, so how else might you see an empirical formula? Well, it could be a hydrate problem. And a hydrate is some ionic compound surrounded by so many water molecules. So instead of looking for the mass of each element, you're going to get the mass of water, and you're going to get the mass of the ionic compound by itself. You're probably going to be given lab data. So you need to get the mass of the water by itself, and usually that's going to be the mass loss, because what we do to find the empirical formula of a hydrate is we heat it up. When we heat it up, the water evaporates and left with the ionic compound. So the mass lost in a hydrate problem will be your mass of water. The mass of the salt by itself should be the mass of the salt and the crucible after heating, or whatever the container is. Because after you finish heating up that hydrate, the water will evaporate, and what you're left with is the ionic compound by itself. So once you have those two masses, you go to moles, divide by small, multiply till whole, which you probably will not have to multiply. All right, then there's also combustion problems. So if that happens, usually what it is some hydrocarbon has been combusted, and you don't know what the formula is. So it could be C2H8. I mean, it could be not H8, but it could be something else. It could be anything with carbon and hydrogen. Well, you produce CO2 and water when you combust a hydrocarbon. So you could actually be given some amount, so many grams of this, and then so many grams of this. What you have to do, because the carbon comes from this, and then the hydrogen comes from this part, is you need to figure out, of this many grams of carbon dioxide, how much is just carbon? And of this many grams of water, how many grams are just water? And you can use the percentage, the percent composition of carbon from carbon dioxide to find that. So that means carbon has a mass of 12. If I find the percent composition, so if I find the percentage of carbon in carbon dioxide, carbon's mass is 12. Carbon dioxide's mass is 44. So 12 divided by 44 will give me my percent. So once I have that percentage, well, the amount of carbon in that amount is whatever this percentage is of that. So that is, if you have a combustion problem, you're going to have to go from your carbon dioxide 2 grams of carbon, and then from your water 2 grams of H, and then at that point you can just simply get your number of moles, divide by small, multiply till whole. And I have an example of this video in another video under, I believe, Unit 2, if you have forgotten it. All right, so another question that they could ask you is about the purity of a substance. So you might be asked to give a percent of something, of a compound or a substance in some sort of mixture. So anytime we're finding percentage, we find the mass of the pure compound or that substance, and then divide it by the total mass of that substance or mixture. All right, so this is an example of a problem. So I did forget to give you the equation here. I didn't give you the full prompt. I'm just giving you the data for this. So when I look at this old problem, you probably want to go ahead and write down what the equation should be. It is 2Ki plus lead nitrate. And they may ask you to come up with this equation on the test too. PbI2. Okay, so in this particular problem, we're given a Ki tablet. Well, inside that tablet, we have potassium iodide, but we also have some filler, some junk in there. So when we take the mass of that, it's 0.425 grams. It's not all potassium iodide. Well, I want to know the mass percentage of the iodine in this tablet. So in order to get the mass percent of iodine in the tablet, I would have to have two amounts. I would have to have the mass of iodide. Iodide is the ion, not I2. I minus because it's iodide if it ends in IDE. Oh, I'm sorry. This should be iodide. If it ends in IDE, that means it's an ion. And clearly right here, potassium iodide, that is an ion. All right, so we have this tablet. I need to get the mass of I, and I need the mass of the mixture, which in this case is going to be this tablet that I'm analyzing. Well, basically, what we did is a precipitation reaction. We combined our potassium iodine with lead nitrate, and then we made potassium nitrate and then lead iodine, which is a precipitate. So I made a precipitate here. So what I did is I precipitated out the iodide. So I have, at the end of this, I have weighed it out with filter paper. I've weighed out lead iodine. So I lead iodide. So when I'm looking at this, I have the mass of the tablet. I also have the mass of PbI2 with filter paper, of course. So what I'm going to do is I'm going to go from my lead iodide. So I'm going to go from my mass of this, and I need to get iodine. So I'm going to use some stoichiometry here. I'm going to go to moles of lead iodide. And then from that point, I can go to moles of what I'm really looking for, which is the I. All right, so first thing, let's get the mass of the lead iodide by itself. So it's going to be 1.698, but this is with the filter paper, so let's subtract that out. And I have 0.236 grams of lead iodide. Well, the thing is, the reason we're looking at this is because all of this iodine had to have come from this tablet. So we're going to use this amount to go back and figure out how much iodine I originally started with. So when I do this, I need to go to moles of lead iodide. One mole is equal to 461. And then I'm going to go to moles of iodine. Well, you might say, okay, iodine's not in this equation, not by itself, but I can figure it out based on this. For every 1 mole of this lead iodine, I have 2 moles of I minus for every 1 mole of this I have. Okay, so now when I go through, I'm going to do the mass. Or actually, I still need to go one more step. I need to go and get the mass. So I'm going to keep going. I'm going to multiply this by the mass of iodine. 1 mole of iodine on the bottom. And the mass of just I is 126.9. Now, a lot of people might forget that this is an ion and not I2. It's not I2. If we're looking at this equation, it's an ion. So it's just 1. All right, so now if I do the math, I'm going to calculate out my mass of my iodine, which is 0.1299 grams. All right, so now I have my mass of my iodine. And I have my mass of my tablet. I just multiply it by 100. And afterwards, I should get about 30.6. They may ask you a problem where you have to give the percentage or determine the purity of a substance. So if you're looking at that, you really are looking at a percentage. You're looking at the mass of whatever the substance is divided by the total mass of the mixture. In this case, we were analyzing a tablet. So usually in these cases, we will do some sort of precipitation reaction and pull out the ion or object of interest. Another question they can ask you in something like this is, why is it necessary to weigh the filter paper multiple times? Well, usually when you have water, what you want to do is you want to heat it or let it dry, weigh it, and then keep doing that until you see that the mass is consistently the same. Once the mass is consistently the same, you can feel confident that there is no longer water in that substance. Okay, another type of problem they might ask you is about density and molar mass. So in order to solve for density, you have to have the mass of that thing and the volume of that thing. Usually a density problem is embedded into a gas law problem. So you would have to have the mass, which is usually something we weigh, okay? And we would have to have the volume of that substance. Sometimes they also ask for molar mass, and if you want that, you have to have the mass, which usually comes from lab data where you've weighed something, and the number of moles, okay? So if you're getting molar mass, remember, molar mass is grams per mole, so you need the mass and to divide that by the number of moles that you have. Density would be mass divided by volume, so you need the mass of that substance and the volume of that substance as well.